Good morning, dear students. So now we are going to discuss on this topic of testability of VLSI circuits. Now, what is testing? Now we know that having designed a circuit, to know that this circuit will perform when when we are subjecting the circuit to proper inputs, proper outputs should result. Okay, so we have to subject the circuit to a number of test inputs and see that proper outputs result. If there is a different things result, then we suspect that some fault has occurred somewhere. Now the circuit complexity has risen day after day. Time required to perform fault simulation and the test vector generation increases with continuing reductions of VLSI dimensions. There has been aggressive scaling, okay, and so when we need to know whether a circuit is performing okay or not, the input vector to which the circuit must be subjected to should be designed very efficiently so that we can capture the actual fault occurring in a particular gate, in a particular combinational circuit. And system reliability and testability must be considered at an early stage of design process. Okay, later on, as the chip goes to the customer premise, before you deliver the final goods, you should subject the device that you have manufactured to a great extent to different testing. Computer aided testing is essential to VLSI design for producing a chip that can be tested exhaustively and easily in reasonable time period. Pattern generation and fault simulation are often based on simple fault models of stacked nodes or gate inputs, short circuits between nodes, or the critical path algorithm. Now what we mean by a stacked nodes, okay, a node is said to be stuck at 0 or stuck at 1 if it remains in a low state or a high state regardless of the logic value asserted. Okay, so that means we say that say for example a gate input for an NMOS transistor, if the gate input remains for whatever reason, suppose there is the disconnection between the metal conductor and the polysilicon gate, there is a disconnection. So then even if we make the gate voltage high with respect to source, the transistor will never be able to come on. So we say that in this circumstance the transistor is stuck at 0. Okay, or suppose the gate plate is somehow shorted to the underlying diffusion. That means even with 0 gate voltage, okay, there is a channel existing. So then we say that that particular transistor is stuck at 1. Okay, so this is one example that we are mentioning now. And testing requires measurement or comparison. So testing requires measurement or comparison which is performed to examine performance of circuits. So it needs a certain amount of measurement and also comparing with what is the desired output. Actual output, if it departs from the desired output, we say that some error is existing, some fault is existing. A node is said to be controllable if its value can be set by the tester to logic 0 or logic 1 or high impedance, that means high Z state. An output node is said to be observable if the tester is able to observe the value of the node level, voltage level. Some key control points in a circuit may be the clock input, the set and clear inputs to storage latches, data select inputs to multiplexers and demultiplexers, and enable and read-write inputs of memory devices, for example random access memory or any memory device. Now what is a fault? A fault is an indication of a manufacturing defect. Okay, so what do you mean by a manufacturing defect? It is not something that is related to the system. It is not because of the particular voltages being applied to a circuit under test. This defect comes from the manufacturing itself. A defect is any source of circuit failure that is caused by physical structure of materials used in integrated circuit fabrication and geometric relationship among these materials. The basic circuit defects include junction leakage, high contact resistance, metal voids causing open circuits, unwanted short circuits between conductors, or leakage through dielectric layers. Okay, so that means when you do not want a device to have such defects, but somehow they can find place. Okay, so it is an indication of a manufacturing defect. A fault is an indication or a manifestation of a manufacturing defect. Now, let me tell you something. It is easier to test a combinational circuit rather than a sequential circuit. Combinational logic is relatively easy to test by applying sets of input signals to the circuit and comparing the outputs produced with the calculated outputs. Sequential circuits, why are they more difficult? Because their outputs depend not only on the present inputs but also on the past set of inputs. In other words, the history or internal state of the circuit. It is necessary to convert sequential networks to combinational networks to test the to test the sequential circuits. One must ensure that all registers are locked and checked. That means we can test the performance of every register, every single register existing in a sequential circuit. In order to ensure that normal operation of the circuit is not held up while testing parts of a sequential circuit, it may be required to insert multiplexers to electrically isolate parts of the circuit for testing purpose. That means by means of using multiplexers judiciously, you can convert a sequential circuit to combinational circuit and thereby apply the principles of testing combinational circuits to those isolated parts of the sequential circuit. Let us show how. We show the serial shadow register approach to test a sequential network. Here you see, in general, if you recall what is the model of a sequential circuit, you have got a combinational logic, and what are the inputs? The inputs are primary inputs, the present state inputs, okay, and the outputs are two broad categories of entities are there. One is the primary outputs and the other category is next state inputs, and next state variables, okay. And here this multiplexer is kept, okay, in order to disconnect the path from the combinational logic output to the state register. See multiplexer means if the mode input or the control input is such that you can get this input directly to the output, then it is a normal operation. See that multiplexer should be kept so that the normal operation of the circuit is not hampered. Okay, that means if you want, the normal operation can go on. At some other point of time, if you want to test the circuit, then the state register we should check, and all the flip-flops existing in the state register should be checked. The serial shadow register diagnostics method converts a sequential network into a combinational network by applying a duplicate or shadow register. So this duplicate or shadow of the state register is what? You can insert values from the state register to this shadow register. See, this shift register should have the serial input serial output ability or parallel input parallel output ability. So by loading this shadow register from the state register, you can load a particular state into the shadow register, okay. Then the output can be fed to the output, this combinational logic, this present state can be fed either from the state register or the shadow register. So if you feed in the data from the shadow register, then the combinational logic gets a particular state value, and depending on the primary inputs, it should produce the proper next state variables. So whether the next state variable is proper or not, you can test. First, you should test the shadow register itself. Okay, so this multiplexer, what it does, it breaks the feedback path by selecting the shadow register. Okay, so that means this state register, its output is normally fed to the combination logic, but if you feed the multiplexer, this path is broken. If first of all, if the shadow register, how it is tested itself, so there is a serial data input SDI and a serial data output SDO. So all possible, suppose this is a 10-bit register, so 2 to the power 10 possible inputs are there, all possible values. So you feed in the values one by one and check the outputs. If the serial data output happens to be a mirror image of the serial data input over the stream of bits that has the same length as that of the shadow register, then we say that we can certify the shadow register to be okay. After that, you make use of this shadow register to perform its operation for which it was kept. The shadow shift register is self-tested by shifting data through its serial ports. After that, it can be used to test other parts of the circuitry. The state information is loaded into the serial or shadow register, and it can be transferred into the internal state register by selecting the multiplexer and clocking the state register. This allows any internal state to be set to a desired value in a simple manner by establishing a logical path for which inputs can be controlled and outputs observed. This reduces the sequential network to a combinational network. Suppose you are suspecting that for a particular value of the state register, say the state register has got a 5-bit number. Okay, so when the 5-bit number is inputted into this combination logic block, the next state values should be proper as well as the primary outputs. But suppose you are not getting the desired value, so what we do, we load the shadow register with a particular value of the state register and feed in the output to the combination logic. Then you check whether the next state value is okay or not. If this is okay, then fine, it gets through this, and then the next state again it is loaded to the shadow register, and so on until you find that for a particular state value the primary outputs are not okay or the next state values are not okay. So then your focus will lie on correcting that particular state value. So for this, the shadow register will be helpful. So it allows us, suppose there are say no less than 20 states for a particular machine. In fact, for commercial machines, it can have no less than say 1000 states. So in a particular state, if the things go wrong, so at some random time you may have to load the 100th state. So for that, the shadow register will be useful. Okay, so you know that what is the 100th state value, so accordingly through serial data input you load the value and then feed it to a combination logic and test where the outputs go wrong. Okay, so this is one mechanism by which a sequential circuit can be converted to a combinational circuit, and then we can subject it to testing. This is one approach. Another approach is scan path approach. In scan path approach, which is also employed to test a sequential circuit, the logic network is transformed into a shift register and tested. If all the flip-flops are controlled and observed, then the test generation process becomes just like that of a sequential network. Okay, a modified D-type master-slave flip-flop with two-phase non-overlapping clocking is taken as the basic memory element. Note that if this is a master-slave flip-flop, the D flip-flop, then you have a separate slave clock which can be derived from the master-slave. Okay, so it is a two-phase non-overlapping clock. In fact, to reduce the wearing, you do not feed a separate slave clock. You can generate the slave clock from the master slave for the master clock itself. Okay, now the output of a 2-to-1 multiplexer, which is built using the 2-input AND gate and the 2-input OR gate and an inverter that we have shown it here, it is attached to this D-type flip-flop. So that means this D-type flip-flop is augmented, okay, is enhanced with the addition of a 2 to 1 multiplexer. Now why do we do so? The reason is that we may subject this D flip-flop to testing by random bits. So for that there is a scan input and the normal data input is this one. So whenever and suppose all the flip-flops are attached one after another in a cascaded manner. So suppose we are showing a 3-bit shift register. That means if the output of every flip-flop is fed to the input of another flip-flop, and the output of that second flip-flop is fed as an input to a third flip-flop, and so on. If you can do so, then in essence in the process you get a shift register, and you need to test that particular shift register through the inclusion of a 2 to 1 multiplexer to each of the D flip-flop. So there is a normal data input and there is a scan input, and based on the mode select value you subject the device to normal operation or to scan operation. Clear? Okay. The mode select input is used to choose between the normal or scan mode as shown in the top figure. As shown, the output of each flip-flop is connected to the scan input of the next flip-flop in the scan register. Okay. Scan register chain, in fact. Why do we call it a chain or a linear chain? Because of the fact that the output of a flip-flop is connected to the input of a flip-flop, and the output of that second flip-flop is connected to the input of a third flip-flop, and so on. To ensure scan testability of a sequential circuit, all flip-flops should be connected in a shift register manner, and such a shift register should have a primary input and a primary output in the scan mode. So in general, if you connect a 4-bit shift register, from the leftmost input it can be a scan input entry, and from the outermost flip-flop the output of that flip-flop can be a scan output. So you subject it to say a 4-bit register, so 2 to the power 4, 16 possible test patterns can be loaded into the shift register, and you see one by one whether all the flip-flops are operating correctly or not. So by testing the individual flip-flops, if you find everything is okay, then you can certify the circuit as okay. Otherwise you can get which one particular flip-flop is malfunctioning, so you can take it out and replace by a proper flip-flop. Okay. Now in general, you see that a test pattern of alternating ones and zeros, normally it is a bivalued flip-flop, so the output can be either 1 or 0. So if you feed in a test pattern of alternating ones and zeros, then you succeed in testing the shift register to all possible input patterns. That's why we say that a test pattern of alternating ones and zeros shifted through every flip-flop of the scan or shift register is considered adequate to detect the faults in the shift path in the master slave flip-flop. So that test pattern of alternating ones and zeros shifted through every flip-flop of the scan or shift register is considered sufficient to detect the faults in the shift path and in the master slave flip-flops. Clear? Now let us discuss about the testing of stuck-at faults. Normally this stuck-at faults is probably the most often used fault pattern. Electrical failures due to physical defects may be grouped into 3 categories. One is open circuits, the next is short circuits, then you have got stuck-at faults. Okay, stuck-at faults can be stuck-on faults or stuck-open faults, and are caused by overstress, breakdown and ionic contaminations. Note that we have studied earlier that overstress means what? If you subject the gate to source voltage to be very high, if you are subjecting the gate to source voltage to excessively high voltage, then dielectric breakdown can occur, and thereby the gate can be shorted to the source or drain, and a channel can lie to exist without even subjecting the gate to proper threshold voltage. So that is tantamount to a particular fault. We say that it is a stuck-on fault. That means even though the gate voltage we have not applied a threshold voltage, but still a channel has come to exist there. Okay. Or we can have a stack open fault. Stack open fault means what? Stack open fault is that suppose there is a breakage, there is a disconnection between the outermost metal conductor and the polysilicon gate. So even though you are increasing the voltage to gate, even exceeding the threshold voltage, the channel can never like to exist for an enhancement transistor. So we say that the device suffers from a stack open fault. Okay. So it can be an open circuit fault, short circuit fault, or stacked fault. And ionic contamination means that somehow the ions find place into the into the gate dielectric, and thereby a channel can come to exist. That is also undesired. Stack-on faults cause the MOS transistor to remain conducting regardless of the gate input voltage. The test pattern for a stack-on fault creates a path between the power supply VDD and ground within the faulty logic gate, and the output takes on a voltage level between the ground and the power supply. Okay. And so that is as per the transistor defect. There can be interconnect defect also. Many interconnect failures can occur due to short circuits between the metal and diffusion lines or breaks in metal polysilicon crossovers. That means there can be a short circuit, that means undesired connection between metal and diffusion when it should not happen, or there is a break or disconnection between the metal and polysilicon. Both are undesired. And field effect transistor failures are often due to gate to drain short circuits. You know that when gate and drain are shorted, then the transistor always behaves like a saturated transistor. So never you can make the transistor behave like a linear transistor, even though you require for digital operation. So always it will behave like a saturated transistor, fit enough for analog operation. Or gate to source short circuit, always off transistor unless there is a implanted channel. Then it is tantamount to a depletion mode transistor. But for an enhancement mode transistor, only when the gate is subjected to a voltage greater than or equal to threshold voltage, then only the channel should exist. But if there is a short circuit, then in absence of threshold voltage also, the enhancement transistor will come to have a channel. That is also undesired. Okay. Or there can be a gate to substrate short circuits. Some of these faults are difficult to model, difficult to detect, but it can be also modeled as stacked faults. Testing of stacked faults, how it is done, we are showing by means of an example. Can be performed by applying proper input test vector. Suppose we have got a CMOS NAND gate. That means two PMOS transistors are in parallel and two NMOS transistors are in series. Now the top NMOS transistor suffers from stack open fault. Stack open means what? There is a breakage between the outermost metal conductor and the gate polysilicon gate. So even if you make the voltage A higher than threshold voltage of a MOS transistor, there will be a breakage and there will be a disconnection between the drain and the source. There can never lie a channel. So how to test it? First, the test vector means an input pattern. That means what voltage value you should apply at the two inputs. Okay. So for a two input NAND gate, the test vector would obviously be of length 2. If a test vector TB1 of 0, 0 you apply to the NAND gate, what happens? You see that by means of the two PMOS transistor conducting, the output voltage will go to high state. Then if the second test vector TB2 of value 1, 1 it is applied, ideally what should happen? The output voltage should come down to ground. But as this top transistor suffers from a stack open fault, stack off or stack open, whatever, then this transistor cannot conduct, and even though AB equal to 1, 1 is subjected for a long time, then this voltage would be somewhere between the VDD and ground. It will never go to perfect ground. Okay, there are some normal reverse bias diode path within the transistor, so by that the voltage can leak to some extent, but never it will come to perfect ground. That's why we have written, if the test vector of 0, 0 is followed by a second test vector of 1, 1, the output is in high impedance state. That means neither 0 nor 1, because both the pull-up devices and the stack open pull down device will be off. Only the bottommost transistor will be on. So this path, the drain of the bottommost transistor will be at perfect ground, but beyond that this ground cannot propagate. So test vector sequence TB11 equal to 0 followed by TB2 equal to 11 will detect the stack open fault of this gate. That means when we find that the output voltage comes to lie either in logic 1 state or in high impedance state, okay, but never in the perfect ground, even though you have applied AB equal to 1 1, so stack open fault lies, okay, in one of the NMOS transistors. Now, so this is one particular example. In general, if we are on the lookout for a general approach procedures, let us say, how to derive test vectors for stack open and stack on faults. So this you have shown a stack open fault. Stack on faults also can happen. That means the channel is already existing even though the threshold voltage, even though the gate voltage is below the threshold voltage. So both can occur. And remember that the threshold voltage for an NMOS transistor is positive, whereas the threshold voltage for an PMOS transistor is negative. Okay. So first step is that provoke the fault by applying an input 0 to NMOS transistor that is stuck on. Note that NMOS transistor, if it suffers from a stuck on means what? Already a channel is existing. So now if you apply input 0, normally it should behave that the voltage should be such that the corresponding to a non-conducting transistor, the voltage should be there. Okay, but if you apply 0 and the transistor is faulty, that means it suffers from a stuck on fault, then the output will be corresponding to a faulty transistor, right? So you provoke the fault by applying a voltage which is opposite to that which corresponds to the defect, so that you get an output different from a normal output. Okay, so it can have a correct output, it can have a faulty output. In order that the faulty output comes on, that's why we are provoking the fault by applying an input 0 to an NMOS transistor that is suffering from stuck on effect. Or for a PMOS transistor, you remember that PMOS transistor, when the input is 0, then the channel comes to exist. But suppose the PMOS transistor is suffering from a stuck on defect, then you should apply logic 1. Clear? On the other hand, suppose the NMOS transistor suffers from a stuck open fault. Stuck open means what? Even though the voltage is greater than threshold voltage for a NMOS transistor, there should not be a channel is stuck open. Stuck open means that even though the NMOS transistor gate voltage is higher than threshold voltage, still channel cannot be formed. That is a stuck open. So that's why, as you suspect that stuck open fault can be there, so you have to apply a input voltage which corresponds to the existence of a channel. Since you suspect that no channel exists, so hence you apply an input corresponding to the existence of a channel. That means the opposite voltage. Similarly, for a PMOS transistor, we know that if it suffers from a stuck open fault, so if you apply logic 0 voltage, channel should come to exist. Okay, so as channel is not existing, so you apply the opposite voltage. That means 0 voltage means for a PMOS channel, for a PMOS transistor, the channel will come to appear. But if the channel is no longer able to exist, then you should apply 0. Okay, right? So that first step is very important. Provoke the fault by exciting the opposite input that you suspect the device to suffer from. So if for an NMOS transistor, if it suffers from a stuck on voltage, apply 0 voltage. If it suffers from stuck off voltage or stuck off defect, apply logic 1 to NMOS, and opposite voltage to the PMOS transistor. Okay, so that if a PMOS transistor is suspected to suffer from a stuck on voltage, you apply logic 1 voltage. If a PMOS transistor is suspected to suffer from a stuck open fault, you apply logic 0 voltage. Okay, because in ordinary circumstance, channel would appear, but if as the PMOS voltage channel cannot exist, so you apply so that you provoke the fault. Okay, so in that circumstance, the output will be different from an expected output. Thereby you can catch the defect, you can capture the defect, you can detect the fault, right? Step 2 is what? See, in general there can be multiple paths, okay, from inputs to the output. Sensitize the path to which the transistor under test belongs. Sensitize means that from the fault location or the fault site to the output node there can be long path, and there can be other paths also. So what you do, sensitize the path so that the effect of the fault can be felt at the primary output, okay, so that the fault can propagate right up to the output node, because you can observe only the output node. Okay, my dear friend, you are not able to observe or read the value of the intermediate nodes, only the output node. That's why the path should be sensitized so that the fault from the fault location or the fault site, the effect of the fault can be propagated right up to the output node. We shall show one example immediately, don't worry. And final step is what? Ensure that the output changes only as a function of the given signal change by allowing no other paths between the appropriate supply rail and the output node. In other words, desensitize all the other paths. Sensitize only the path from the actual fault location to the output and desensitize all the remaining paths. Okay, let us see one example. See, in fact here we are showing one example where whatever comes to us by common sense reasoning, that we are keeping. Say we are showing a CMOS gate, a static complementary CMOS gate, as you can see, and the output also I have written for your benefit, and you can easily get it that from the configuration of the PMOS subcircuit and that of the NMOS subcircuit, you can understand that the logic of the output voltage is what? A ANDed with the ORing of B and CD and complement of that. Okay, so this particular function is being implemented by this static circuit. Okay, and the 4 test vectors shown in the table will potentially test for a stuck-on fault at the device. Again, what is a stuck-on fault? If you recall, stuck-on fault means even though this is an NMOS transistor, so if you make this logic 0, okay, the source and drain are connected by means of a channel. Somehow there could have been a short circuit between the polysilicon gate and the underlying diffusion source and drain, so that a channel is already existing even without the gate getting a voltage bigger than the threshold voltage. So ordinarily the channel should not exist, but even though with even if that is the case, even though a channel should not exist in ordinary circumstance, now if you apply the gate voltage to logic 0, still a channel is somehow existing, so that means we get wrong result. Okay, so these are the 4 test vectors to which the circuit is subjected. ABCD, there are 4 inputs, so 0 1 0 0, as you can see, what should be the desired output? Acha, 0 means what? The output, correct output should be high, because this PMOS transistor is working, so the VDD is available at the output node. Okay, and 0 1 0 0 means as this transistor is off, so there can be no path between the ground and output node. So this output voltage, the correct output expected should be logic 1. But as this is stuck on, faulty output can be obtained as 0, right? And why it is so, if you can question me, I can give you the answer. The answer will be available if you can look at this circuit as a resistive network. Okay, so my dear friend, if you can recall that for 130 nanometer process, and whatever we have understood in the class is that if the transistors are of unit size, that means the length and width are of value 1 1, the feature size, then what is the resistance offered by an NMOS transistor? It is 12.5 kilo, whereas for a PMOS transistor it is 30 kilo. Okay, 2.4 times larger. Clear? I believe all of you can recall, right? So you see, this is the resistive network, equivalent resistive network for this circuit. Okay, so we have specified 4 test vectors: 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 0 1 1, but 3 of them succeed in detecting the fault, whereas the fourth one 0011 may not be able to capture the fault. Why? We answer the question by means of looking at the equivalent resistive network. So with 0100, what is the resistive network equivalent sub-circuit? You have got a PMOS transistor or a single resistance of value 30 kilo ohm, whereas as this is stuck on, so this provides 12.5 kilo ohm and B is also 12.5 plus 12.5, 25 kilo ohm. Okay, so 25 kilo ohm in the pull down resistance and 30 kilo ohm is the pull up resistance. So that means roughly it is lower than the 50% value. So it may be the inverter. See, in ordinarily this is a inverter. So inverter output can be 2.27. So if this the output voltage is 5 volt, the power supply voltage is 5 volt, any voltage lower than 2.5 volt will be recognized as a logic 0 voltage, whereas any voltage in the range from 2.5 to 5 volt will be treated as a logic 1 voltage. So here it will be read as a logic 0. That's why the faulty output we are writing as a 0, but correctly the output should have been logic 1, okay, or perfect 5 volt. But because of the stuck on fault occurring at this transistor, it will be 2.27 volt as it is lower than 2.5 volt. So we shall take it, we shall read it as logic 0. Similarly for the other two test vectors also, so 0, 1, 0, 1, that means in all there are only two resistances of value 12.5 kilo ohm in series or equivalent resistance of 25 kilo ohm in the pull down path, whereas for the pull up path it is 30 kilo ohm. So in all the three cases corresponding to the test vectors 0100, 0101 and 0110, which happens to correspond to the presence of two NMOS transistors in series, okay, A or B, A and B, okay, like that, or say for example, if B is on, in this case you see B is on, so although C and D are not all together on, both are not on, so the path will be like this, current path A followed by B, okay. So always two transistors will be on in series path. So that means 12.5 plus 12.5 or 25 kilo ohm for the pull down resistance, or the pull up resistance, a single resistance of 30 kilo ohm. So 30 kilo ohm in the pull up resistance, 25 kilo ohm in the pull down resistance, you get 2.27, which is lower than the 50% of 5 volt, so it will be read as a logic 0. But for the fourth one, TV4 equal to 0011, you see that both transistors are on. That means no less than 3 transistors are on. No less than 3 transistors means 12.5 into 3, that means 37.5 kilo ohm, right? 37.5 kilo ohm in the pull down path, whereas the pull up path is only 30 kilo ohm. So now the pull down path will be able to pull down the voltage lower than the, it will be able to pull the voltage above the 50% point, because 37.5 kilo ohm is the pull down path, 30 kilo ohm in the pull up path. So 37.5 divided by 30 plus 37.5, so it is 2.78. 2.78 is definitely above the 50% or 2.5 voltage. So that means it will be treated as both the faulty output and the correct output will be same. So then TV4 is not a fit candidate for a test vector. You see that the test vector will be proper if we get different outputs, one for the faulty case, one for the correct case, okay. So erroneous output should be different than the correct output, then only we can certify the test vector as proper one. So TV4 we cannot certify as a proper test vector, only the first 3. Is it clear? Okay, so first 3 test vectors are clearly the fit candidates for test vector, whereas the fourth one is not a proper test vector. Okay, that's then our inference is that TV4 fails to detect the fault, whereas the first 3 test vectors, namely TV1, TV2 and TV3, are able to detect the fault. Clear? I believe it's okay. Next, what we go, so far we have restricted ourselves to ad hoc technology. That means somehow we are able to capture the test vector, but it is an inexact method, okay, a trial and error method. Now we are on the lookout for an exact technique. For that, Boolean difference is a very important mathematical technique. It is an algebraic technique for developing test patterns for combinational circuits. It is a method of determining the primary inputs, that is the test vectors required to force a function to be sensitive to a particular input variable. Boolean difference is an exact method of generating the test vectors as opposed to techniques of path sensitization based on trial and error. Path sensitization methods are also somehow popular, like PODEM, say path oriented decision making procedure is there. Those are also popular, but this is mathematically clearly have an edge. You can get the exact test vector by applying Boolean difference. So let us study the basics of Boolean difference. First, the definition. Boolean difference of a function y with respect to a variable x is defined as dy dx equal to y subscript x corresponding to 0 value XORed with y corresponding to x corresponding to 1. Now what is y subscript x of 0? This is the value of y when x is given the value 0, and y subscript x of 1, it is the value of y when x is 1. Now if an output y is sensitized to a variable x, and if the variable x is toggled, that means once it is 0 and other time it is 1, then the output y should toggle, right? Y would be different in the two cases. If the output does toggle, then y is 0 and y is 1 will definitely be different. Okay, that means that this XOR value will give rise to the value 1. So dy dx equal to 1. We indeed require dy dx to be 1 if we have to make y to be sensitized to a variable x. Let us apply it to a 3 variable case. Take a function y of abc equal to this: a bar bc bar, ab bar c bar, and abc. These 3 product terms are there. Find dy dA, the Boolean difference of y with respect to a, that is dy dA, and show that the value of y indeed depends on the value of the variable a when b equal to 1 or c equal to 0. So b equal to 1 or c equal to 0, these are the conditions that must hold so that y becomes sensitized to the value of the variable a. Okay, that means with toggling of a, y should also toggle. That means with a taking up differing values, y should also do the same thing. Clear? Let us see. So you have taken down the expression. What is dy dA from the definition? It is the exclusive OR of y subscript a corresponding to value 0 and y subscript a corresponding to a having the assume the value 1. So you see that when a takes the value 0, then these two second and third terms reduce to 0. So what is left out? The coefficient bc bar. Okay, and y when a takes up the value 1, the first term vanishes. From the second and third term we get it is the equivalence of b and c, or b bar c bar or with bc. So this is y a corresponding to 0. This parenthesized expression, sub expression, corresponds to y a corresponding to value 1. Now if you do the XORing, then bc bar corresponding to a complement of this, so that is the exclusive or bc bar plus b bar c. And what is the complement of bc bar? That is b bar or with c, and the same thing b bar c bar or with bc. You do the algebraic manipulation, you find it to be b or with c bar. I have used an absorption theorem from this to this. All of you are well aware of the basic Boolean theorem. That means a or with a bar b gives us a or with b. So a bar vanishes, a bar is absorbed. Similarly, c bar or with c and with b gives me c bar or with b, or b or with c bar. Now to show that if b equal to 1 or c equal to 0, then y indeed depends on a. When b equal to 1, in this case, look at the original expression, what it reduces to. If b equal to 1, this vanishes. Okay, this remains a bar c bar ANDed with ac. Okay, so then a bar c bar ANDed or with ac. Now with b equal to 1, if you make a equal to 0, what it reduces to, it becomes C bar. Whereas if with B becoming 1, if you now make A, force A to 1, then this becomes C. So C bar is definitely different from C. Thus when B equal to 1, Y changes whenever A changes regardless of the value of C. Similarly, you see that if C equal to 0, then Y reduces to, from the original expression, if C equal to 0, then A bar B will remain and A B bar will remain, this term vanishes. So A bar B or with A B bar. Now Y, if you force A to 0, okay, and B to 0, what happens? This becomes B. I'm sorry, if C is already 0, now you force A to 0, B is the only variable, so it becomes B. Whereas if you now force with C equal to 0, you force A to 1, then it becomes B bar. So B and B bar are definitely different. So when C equal to 0, Y changes whenever A changes regardless of the value of B. So that means Y is made sensitized to X. Okay, that means the function Y can be made sensitized to X by forcing the condition such that dy dx equal to 1. In the above example, by making B equal to 1 or C equal to 0, Y is made sensitized to X. Clear? Now we make a very important mathematical definition. Please pay attention. We need to develop a set of test vectors for a function with a primary input stuck at 1 fault or stuck at 0 fault. The path must be sensitized that will exercise the fault when that variable is set to 0. Now this is very important. To develop a set of test vectors for a function with a primary input variable stuck at 1, then a path must be sensitized that will exercise the fault when that variable is set to 0. So for a NMOS transistor, as we recall, that if it is stuck at 1 means that already a channel is existing. Okay, so we have to make the voltage, gate voltage, equal to 0, right? Okay, why? Mathematically what we do, X bar ANDed with dy dx equal to 1. This we should, the test vectors must satisfy this. That means the test vectors or the primary input test patterns which should be able to test for the primary input variable stuck at 1 should satisfy x bar dy dx equal to 1. Why? Because x bar equal to 0 only when x equal to, see, x bar equal to 1, I'm sorry, x bar equal to 1 only when x equal to 0, right? So you have to set the variable to 0 so that you can test it for stuck at 1 fault. And dy dx is the condition which must be true so that y is sensitized to x. That means the output should differ in the faulty condition and fault free condition. Remember that test vector, an ideal test vector would be such that the output should produce differing outputs, once when in faulty condition and when in fault free condition. So outputs must differ in the two conditions, in faultless condition and faulty condition. So dy dx should be 1 so that output is sensitized to x, and x bar should be true. X bar should be true means x equal to 0. That means you have to set the variable to 0 in order that you can test for stuck at 1 fault for that variable. Correspondingly, for the stuck at 0 fault for this variable, the variable should be set to 1. Again, you understand from the physics, from the physical occurrence, when a transistor, say NMOS transistor, it is at stuck at 0. Stuck at 0 means what? Even though you set the voltage to high, okay, channel cannot exist because somehow the outermost metal conductor is disconnected from the polysilicon gate. So even though you are making the gate voltage high, channel can, the transistor always remains cut off. So in order to test a cut off NMOS transistor, the gate voltage should be made to logic 1. Okay, why? Because the output voltage, whatever be the value where the transistor conducting, will, that would have given some particular value, and now that the transistor is suffering from the fault, definitely the output will be something different. Okay, right? So the path can be sensitized that will exercise the the fault. That means a particular transistor is suffering from a stuck at 0 fault, then the corresponding input should be set to 1 for a NMOS transistor, my dear. Okay, for a PMOS transistor it will be different. And mathematically x dy x should be equal to 1. That should test for a x stuck at 0 volt. I think it is clear. So this corresponds to x dy dx equal to 1 for an NMOS transistor. Stuck at 0 means there is no channel even though you are applying gate voltage to high. So for that you must apply the input to high, logic 1, right? So that if you sensitize the path, that means the effect of the transistor fault can be propagated right up to the output. So output value will differ in faulty condition and fault free condition. The two values of the outputs will be different. That's what we want. Okay. Now see one example. In this circuit, on the adjacent figure, we show a 3 variable majority function being implemented by this circuit consisting of 3 number of 2 input AND gates and 1 number of 3 input OR gates. And note that each variable is occurring as input to 2 distinct inputs. So A is occurring as input to gate 1, gate 2, B is occurring as input to gate 1 and gate 3, C is occurring at gate 2 and gate 3. Now whenever you test for A stuck at say stuck at 1, the test vector should test separately for gate 1 and gate 2 because A is appearing both at gate 1 and gate 2. So the set of test vectors must be able to test separately for fault occurring here and fault occurring here. Okay, let us see. So in this particular problem we are asked to find all the test vectors required to test the input C. C is occurring in gate 2 as an input, gate 3 as an input. So the set of test vectors that we shall generate must be able to test both gate 2 and gate 3. So first of all, the algebraic expression is this. Recall that dy dc equal to the Boolean difference of y with respect to C is y when C takes up the value 0 XORed with the value of y when C takes up the value 1. And what is y value when C takes up the value 0? That is AB. When C is equal to 0, right? Because second and third term vanishes, only AB remains. And when C equal to 1, C equal to 1, that means AB ORed with A ORed with B. So it is A ORed with B. And dy dc equal to XOR of AB and A ORed with B. So you do that, you find it is A ORed with A bar and it will be ORed with A B bar. So exclusive OR of A and B. Now for C stuck at 0, if you recall, the set of test vectors must satisfy this condition. Stuck at 0. Okay. So that means somehow this input is cut. There is a we cannot see by bare eye. So somehow this wire is snapped. So even though if you apply logic 1 here or logic 1 here, this will behave like a 0 input. That is the thing. So stuck at 0 means even though if you apply 1 here, this will behave as a 0. So you have to exercise the fault by applying C equal to 1. So C dy dc equal to 1, that should be satisfied by the test vectors that will test input C for stuck at 0 fault. Clear? The stuck at 0 fault is occurring in input 3, I mean gate 3 and gate 2. So test vectors must satisfy C dy dc equal to 1, or the test vectors we write it like. So A bar BC means A equal to 0, B equal to 1, C equal to 1. And A B bar C means A equal to 1, B equal to 0, C equal to 1, corresponding to A B bar C. So two test vectors are there. And for stuck at 1, similarly C bar dy C equal to 1. So we get it like A bar B C bar or with A B bar C bar. So A bar B C bar corresponds to test vector 3 TB3 0 1 0 0 1 0, and A B bar C bar means 1 0 0 1 0 0 TB4. Okay. For the test vectors TB1 and TB2, which are intended for testing the input C for stuck at 0 fault, let us see what happens. The correct output is 1. Why correct output is 1? As you can see, 0 1 1 means say 2 input are 1. So BC is 1 means this will give me 1 and output will be 1. So correct output is 1. Or here TB2, A and C is 1. So corresponding to gate 2, you get 1, you get 1. Correct output is 1. But the erroneous or faulty output when C is stuck at 0 is 0. Why? You see that 0 and 1. So E corresponds 0 1 1. This will behave like actually 0 1 0. Right? So you see that at least 2 of the inputs must be 1, so that the output of any AND gate must be 1. If 2 inputs are 0, then all the outputs will be 0 and hence the output will be 0 of the OR gate, gate number 4. So that means the erroneous output or faulty output will be definitely 0. Now TV1 corresponding to 0, 1, 1, it tests C at gate 3. Why do we say so? For that you notice that TV1 corresponds to 0, 1, 1. So 0, 1, 1 means that B and C, for fault free condition, this should be 1. Okay. Whereas 0, 1, 1 as A equal to 0, so this path is desensitized. Although C is applied as an input to gate 2, so as A equal to 0, this is forced to 0, and hence even though some fault occurs here, we cannot capture that. So with TB1 equal to 0, 1, 1, we can capture the defect which occurs only here, not here. Okay. So that's why TB1, 0, 1, 1, it sensitizes this path and desensitizes this path. Okay. Similarly, TV2 equal to 1, 0, 1. Okay, this is also corresponding to the defect, stuck at 0 defect occurring at C, but corresponding to gate 2. So TV2 equal to 1, 0, 1 is meant for testing the defect in C occurring in gate 2, not in gate 3. Okay, because TV2 1, 0, 1 will sensitize this path. Please note carefully, from this path is sensitized by means of TV2 equal to 1, 0, 1, and also this serves to desensitize this path. How? Because B is 0 here. So B equal to 0 means this path is not enabled, this is 0, so this path is desensitized. That is very important. That means the test vector should sensitize a single path and should desensitize all other paths. Okay, so there are 3 paths, only one path is desensitized, the other 2 paths are desensitized. Clear? So TB1 sensitizes only for gate 3 and desensitizes this and this. As A equal to 0, already this is desensitized. TB2 equal to 1, 0, 1. So this sensitizes this and these are first and third are desensitized. Similarly, for the test vector, vectors TB3 equal to 0, 1, 0 and TB4 equal to 1, 0, 0, you can easily understand that this is meant for testing or stuck at one fault occurring at C. Which one for gate 2, which one for gate 3, you can easily tell me. The correct output is 0. Correct output is why 0 that you have tested. That means if more than one input is 0, definitely the output will be 0. So correct output will be 0. But if C is stuck at 1, say B is 1 here corresponding to gate 3, you see that if C is stuck at 1 means what? Already some short circuit is there, that means channel is existing. Okay, this is actually gate input, so it means that somehow there is a short circuit. Even if we apply a logic 0 here, this will behave like a logic 1. That case, you just look at only as a gate input. Okay, here as it is a gate input, forget about the transistor. It means that what do you mean by stuck at 1? Even though we apply a voltage of 0 here, but it will behave like a logic 1. How exactly? That for that some transistor defect is there. So for that matter, we are oblivious of any transistor operation here. We are just when we talk about a stuck at one fault occurring at this variable, this gate input, it means that although we are applying although we are applying C equal to 0, this will behave like a logic 1, right? So 0, 1, 0 means although we have applied 0, this will behave like a 1. So 1, 1 together 1, 0, 1, 0, it will behave like a 0, 1, 1. So you get a 1, you get a 1 here. So faulty output is logic 1 and correct output is logic 0. Okay, so erroneous or faulty output is 1, whereas the correct output is 0. And similarly, TV4 equal to 1, 0, 0, that tests for the stuck at one fault occurring at C. Clear? So this is about the stuck at one fault and stuck at 0. Now, the above technique can also be applied to non-primary outputs of a circuit. Suppose you have got we shall show by means of an example that in the path, see here for example, between A and C there are only 2 gates. Suppose between this and this there can be 3 or 4 gates, many number of gates. So you have to, the entire expression will be very complex. Here it is very simple that AB OR with AC OR with BC, but you can have a very complex expression of output Y, which is a function of A, B and C. It can be a function of more than one, 3 variables also. Then you can simplify the technique of finding the test vector. For that, we apply what is known as chain rule. Okay, that means the above technique can also be applied to non-primary inputs of a circuit. The chain rule of differencing can be applied to obtain test vectors for secondary inputs or non-primary output. The chain rule, what does it say? If a line, output line Y, depends on line M, which in turn depends on line N, that means M is the output for a gate of which the input is N. So as you have learnt in our high secondary days, that chain rule of differentiation, so this is something similar, chain rule of differencing, Boolean differencing. So dy dn equal to dy dn ANDed with dm dn. All these are Boolean operations, mind you, not numerical, not arithmetic operations. Okay, so dy dn equal to dy dm ANDed with dm dn. It may be computationally easier, as you can see, to find dy dn by this chain rule rather than computing it directly. So directly finding dy dn may be more difficult rather than you compute dy dm and dm dn separately and just Boolean AND product you do. One can apply the rule in general to sensitize a logic path of arbitrary depth. So here we show an example. So here the depth of path is 4. Okay, or the logic level of the path is say 4 because the signal travels through 1, 2, 3, 4 gates. Okay, so this is an example of a logic of depth 4. We apply the chain rule to the circuit shown below to find test vectors for A stuck at 1 and for A stuck at 0. So A is one of the primary inputs and V, W, X are non-primary inputs. Okay, and Y is the ultimate output, single output. So what we need to find out, if you recall, A ANDed with dy dA, that gives me the set of test vectors corresponding to testing the appearance of a stuck at 0 fault at A, and A bar dy dA will give me the set of test vectors corresponding to finding the stuck at 1 faults in A. Okay, now by applying chain rule, what we can obtain here is that first V, start from here, so V equal to A OR with B. So what is dVdA? dVdA equal to VA corresponding to 0 XOR with V corresponding to 1. That is very easy. It is B XOR with 1, that B bar. Similarly, W is related to V. Just see, actually Y depends on V, W, X, A, B, everything. But we go in a simplified manner. V depends on A, W depends on V, X depends on W, Y depends on X. So dy dA we can write as simply dy dx Boolean ANDed with dx dw, ANDed with dw dv, ANDed with dv dA. That's why we first find out dv dA. So dv dA equal to v bar. Next dw dv, because w is a function of v, so dw dv equal to c. Then next dx dw, x is a function of w, so dx dw equal to d bar or with e bar. And finally dy dx, so y is nothing but x ANDed with f, so it is simply f. Finally dy dA equal to dy dx ANDed with dx dw, ANDed with dw dv, ANDed with dv dA. So finally you get it like this: b bar c d bar f or with b bar c e bar f. So A ANDed with dy dA, that gives me the test vectors that test input A for a stuck at 0 fault. Mind you, here see there are 6 primary inputs A, B, C, D, E, F, but here E is absent. So how do you write the test vector from this? It is 1 0 1 0, and in place of E we write X. So this corresponds to 2 different test vectors, 1 0 1 0 0 1 and 1 0 1 0 1 1. Similarly, here you see that D is absent. So from this we get 2 test vectors, 1 0 1. In place of D we have written X. So 1 0 1 0 0 1 and 1 0 1 1 0. But mind you, D and E are never simultaneously 1. Okay, so the constant thing is that ABC are 1 0 1 and F is 1. but D and E can be 0 0, 0 1 or 1 0. Never D and E in this example, they are not simultaneously 1. Okay, so 1 1 is ruled out. So in all we get 3 test vectors. My dear friends, you can write out the 3 test vectors, okay, for which correct output is 1 and erroneous faulty output is 0. Why correct output is 1? See, as you have applied A to be 1, so here you get 1, C is 1, so you get 1. Okay, D and E, one of them is 0, you get 0. So 1, 1, and this all gets the 1, 1, and finally F is 1, so 1 and 1. Correct output is Y equal to 1. But faulty output, when A is stuck at 0, so B is 0, so A and B, they together give me 0, then C is 0, 0, 0, 0. Here one of them is 0, so 0 odd with 0 give me 0, 0 ANDed with anything gives me Y equal to 0. So faulty output is 0, whereas the correct output is 1. That's what we are using, for which the correct output is 1 and erroneous or faulty output is 0. Similarly, A bar dy A, that will give me say 3 test vectors again. So here E equal to x, here D equal to x. So 0 0, 0 1 or 1 0, not 1 1. Okay, so for which the correct output is 0. Why correct output is 0? Because A is 0 and B is 0, so you get 0, then again 0, you get the correct output is 0. But if A is stuck at 1, then it will, even though you have applied, you have the applied input is applied input is 0, but as this is stuck at 1, so this will be like a 1. So for the fault, the faulty output will be 1. Okay, that's why I have written correct output is 0, but faulty output is 1. And also you see that there is a single path. This path is sensitized, which to show the sensitized path, I have made the sensitized path as a dotted line. Okay, from A to Y. There are other 1, 2, 3, 4, 5 other paths. All the other paths are desensitized. How are they desensitized? That you can tell me. For this, B has to be 0, C has to be 1. Okay, because for a AND gate, if the C cannot be made 0, right? So B is 0, so that this cannot control. To desensitize this path, B should be made 0, C should be made 1, D or E cannot be simultaneously make 1, so one of them should be 0. So 0 0 or 0 1 or 1 0, and F should be made 1. Then you can desensitize the 5 paths, 1 2 3 4 5. That's what we have written. From the above figure, F equal to 1 enables gate 5. This should be enabled, and gate 3 should be disabled. Okay, and gate 4 should be enabled, gate 2 should be enabled, gate 1 should be enabled. Okay, but gate 3 should be disabled. That's why one of the inputs should be 0. That's what. Then the only single path from A to V to W to X to Y can be sensitized. The other 5 paths are desensitized. So that's all. Now for this this is a very simple discussion on the testability of VLSI. What we have seen, what are the principles of testing we have identified. So principal thing is that the test vector generation, the input test vector, which will be able to capture a defect occurring in a particular transistor or in a particular gate input. So sequential circuit is more difficult to test compared to a combinational circuit. Sequential circuit can be reduced to a combinational circuit by interposing a multiplexer, which by isolating certain paths makes the sequential circuit behave temporarily like a combinational circuit. But its normal operation should not be hampered. For this, the multiplexer is there. Scan path approach and serial shadow register 2 techniques. Then we have identified what do you mean by stuck-at faults. We have given some example, some ad hoc technique. Okay, but ad hoc techniques always are not helpful. So we need an exact technique. For that, Boolean differencing is a very important mathematical algebraic technique, which is an exact technique of generating the test vectors or input patterns for testing a combinational circuit. Okay, so we have shown one example, and then to test the to apply the method for non-primary inputs, and also to simplify the computation of Boolean differencing for a For a multi-level gate, for a multi-level logic circuit, for example, you have shown a 4-level logic circuit. Okay, so we can apply the chain rule of differencing. Okay, that's all for this simple discussion on VLSI testability. That's all, dear friends. If you have any questions, you can write on the chat window, or you can send me any questions by email. I'll be happy to answer that. Okay, thank you for your attention. Thank you, dear friends.